Hello. Welcome to Evening Atlas. Get comfortable. Dim the lights. Close your eyes, if you'd like. Tonight, we're embarking on the longest journey imaginable. A journey through the entire history of the universe. From the first spark of light, to the last dying star. 13.8 billion years, in one peaceful narrative. There's no rush. No urgency. Just the infinity of space, and a gentle voice to guide you through time. From the birth of space and time itself in the Big Bang, through the formation of the first atoms, the birth of stars and galaxies, the emergence of life, and far beyond our present day. Let this story wash over you. Let billions of years become your lullaby. The universe has waited 13.8 billion years to tell you this story. Let's begin. Let's try to imagine something right at the edge of what we can even talk about. Not with those glittering stars we see, or the huge galaxies, but with a universe so incredibly hot and crammed that the very ideas of space and time sort of lose their meaning. When we casually say, the beginning, what we're really doing is pointing to that first tiny fraction of a moment, the earliest our physics can possibly describe. Our current understanding hits a wall there, a kind of conceptual horizon. It's genuinely important to wrap our heads around this. The Big Bang wasn't some sort of bomb going off in space, like a firework in a dark sky. No, it was actually the expansion of space itself. There wasn't any big, empty black void just sitting there, waiting for something to fill it up. Instead, every single bit of space that exists now, every corner of the cosmos we can see and even those we can't, was once squashed together into a state so unbelievably small and bursting with energy that it's almost impossible for us to picture. This wasn't a matter of things flying through a pre-existing container, it was the container itself stretching, growing from an infinitely compact point. If you could somehow run the whole universe backward, just like hitting rewind on an old movie, you'd see galaxies that are now far apart start to drift closer and closer. The huge clusters of galaxies would tighten up, light would get squashed, turning blue, and temperatures would begin to climb dramatically. Keep that cosmic film rewinding, and everything would converge, squeezing into an incredibly dense, almost unimaginable state. Eventually, the math that describes all of this, the very equations we rely on, suggests we'd reach a point where our known laws of physics simply break down. We can trace things back pretty far, but there's a definite theoretical limit. Exactly what happened at that absolute earliest instant is still a big mystery, something we just haven't figured out yet. Our current best theories, like Einstein's general relativity, do a stunning job of explaining gravity when we look at vast scales, planets, stars, galaxies. But they completely fall apart when you try to apply them to things that are unbelievably tiny, like the conditions at the very beginning of the universe. To truly get a handle on that initial moment, we'll likely need a whole new framework, a grand theory that somehow manages to bring gravity into harmony with the strange, fuzzy rules of quantum mechanics. It's a puzzle that keeps physicists up at night, trying to unify these two pillars of modern science. Still, it's quite amazing how quickly our models become surprisingly reliable after that initial, elusive instant. We're talking about a tiny fraction of a second later. From that point on, the universe was definitely expanding and, as it stretched, it was cooling down. Energy was just everywhere, dominating everything. You wouldn't find any atoms, not even atomic nuclei, just an incredibly intense, chaotic field of radiation and countless particles constantly crashing into each other, interacting at speeds and densities that are hard to fathom. It was a universe of raw, unformed energy. Then, something truly wild happened, a short but incredibly dramatic event we call cosmic inflation. In a time span so brief it's almost incomprehensible, far less than even a single second, space itself expanded at an absolutely mind-boggling rate. We're talking faster than light travels today, which sounds like it should break Einstein's rules, right? But it doesn't, because it wasn't objects zooming through space, it was space itself that was stretching and growing, pulling everything along with it. This burst of rapid expansion smoothed out many of the early irregularities. This inflation period helps us make sense of why the universe looks so remarkably uniform no matter which direction we gaze. It explains how regions that are now separated by billions of light-years, so far apart that light hasn't even had time to travel between them, somehow started off with very similar conditions. Inflation essentially took a tiny, perfectly smooth patch of the nascent universe and stretched it out, inflating it into the unimaginably vast and consistent cosmos that we observe today. It's like blowing up a balloon with a tiny dot on it. The dot grows larger, but it stays a dot. But even inflation, for all its smoothing power, didn't make everything perfectly uniform. At the smallest, quantum level, reality is inherently a bit fuzzy and fluctuates. Tiny, fleeting variations in energy are constantly popping into existence and disappearing again. During that incredibly rapid inflationary period, those microscopic quantum ripples were stretched out across truly enormous distances. They weren't just smoothed away, they were essentially frozen into the very fabric of spacetime itself, becoming permanent, albeit incredibly subtle, imprints. Those stretched-out quantum fluctuations then translated into minuscule differences in density. Some regions of the universe ended up with just a tiny bit more energy, a little more matter, than others. These differences were unbelievably small, honestly less than 1 part in 100,000, almost imperceptible. Yet, over vast cosmic timescales, gravity, that patient sculptor, would begin to amplify them, slowly pulling more and more material into these slightly denser spots. These humble beginnings, almost nothing at all, were the raw material from which all the galaxies and galaxy clusters would eventually form. When that extraordinary period of inflation finally came to an end, its immense energy didn't just vanish into thin air. Instead, it underwent a profound transformation, converting into a sweltering, dense bath of countless particles and radiation, a process sometimes referred to as reheating. The universe was reborn, becoming a seething, brilliant plasma, packed with interactions happening at a speed and intensity that our minds can barely grasp, a truly chaotic and dynamic soup. It was as if a calm, smooth expansion suddenly gave way to a boiling cauldron. At this stage, the entire universe was actually smaller than a single city, yet it was already expanding with incredible speed. The temperatures were so extreme that anything resembling familiar matter simply couldn't hold together. Energy was constantly morphing into particle-antiparticle pairs, like an electron and a positron, only for them to immediately crash into each other and annihilate, converting right back into pure energy. It was a rapid, furious dance of creation and destruction, a delicate balance that ensured no stable matter could yet exist. Within this superheated plasma, quarks, the fundamental building blocks that make up protons and neutrons, moved around freely. Physicists call this a quark-gluon plasma. They hadn't yet combined into stable, composite particles. The universe was far too hot, too energetic for them to bind together for any significant length of time. Imagine a restless, shimmering sea of fundamental particles, never settling, always in motion, always interacting, a state of profound instability and constant flux. As the universe continued its rapid expansion, those extreme temperatures began to drop, ever so slightly. Within the first microsecond of existence, something crucial happened. Quarks started to coalesce, joining together in groups of 3. This bonding formed the first stable protons and neutrons. Imagine a restless, shimmering sea of fundamental particles, never settling, always in motion, always interacting, a state of profound instability and constant flux. As the universe continued its rapid expansion, those extreme temperatures began to drop, ever so slightly. Within the first microsecond of existence, something crucial happened. Quarks started to coalesce, joining together in groups of 3. This bonding formed the first stable protons and neutrons. And when matter and antimatter meet, they don't just react, they annihilate each other completely, turning entirely into energy. If the amounts of matter and antimatter had been perfectly equal, absolutely nothing substantial, no stars, no galaxies, no people, would have remained. The universe would have been an empty expanse of radiation. Somehow, and scientists are still working hard to figure out the exact mechanisms and why, the universe developed a tiny, almost imperceptible preference for matter. We're talking about roughly one extra particle of matter surviving for every billion pairs of matter and antimatter that annihilated. That incredibly slight, fundamental imbalance, that almost insignificant excess of matter, is the sole reason that anything exists at all. It's why there are stars, why there are planets, and ultimately, why we are here to wonder about it all. By the time the universe was just 1 second old, most of those dramatic matter-antimatter annihilations had already run their course. What was left was a searingly hot mixture of radiation, ghostly neutrinos, electrons, protons, and neutrons. It was still far too energetic, too turbulent for anything like stable atoms to form, but all the fundamental ingredients, the raw building blocks, were now present and accounted for. The universe was still a plasma, but it had taken on a more defined composition. Neutrinos, those incredibly tiny, nearly massless particles, had decoupled very early on. They began streaming freely through space, barely interacting with anything. Even today, truly vast numbers of these phantom-like particles are passing right through your body every single second, completely unnoticed. They are quiet, unassuming relics, direct messengers from the universe's very first moments, carrying information about conditions that existed when the cosmos was barely a blink old. Over the next few minutes, the temperature of the universe continued its downward trend, eventually reaching a still staggering billion degrees. Now, that might sound like an unimaginably hot temperature to us, and it certainly is, but in the grand, cooling story of the cosmos, it actually represented a significant drop. The conditions were finally gentle enough, just stable enough, for a brief window of nuclear fusion to occur across the entire young universe, happening everywhere at once. For a short, precious window of time, lasting only a few minutes, protons and neutrons began to collide and fuse together. This pivotal period is known as Big Bang nucleosynthesis. And unlike the fusion processes that happen deep inside stars, which would come into play much, much later, this was a spontaneous, universal fusion event, taking place uniformly across the entire, rapidly expanding young universe. It was the first mass production factory for light elements. Most of the protons, however, remained individual, single units, eventually forming the nuclei of hydrogen atoms. Some of them combined, though, creating helium nuclei, each made of 2 protons and 2 neutrons. And a tiny, almost trace amount of lithium was also formed in this brief burst of cosmic creation. Heavier elements simply couldn't appear yet. The universe was expanding and cooling far too quickly for those more complex nuclear reactions to take hold and sustain themselves. When Big Bang nucleosynthesis finally wound down, the universe was composed of a distinct and stable ratio, roughly 75% hydrogen and 25% helium by mass. These proportions, which were initially predicted by theoretical models and have since been beautifully confirmed by countless astronomical observations, remain one of the most compelling and robust pieces of evidence supporting the Big Bang model. It's a foundational fingerprint of the early cosmos. After this brief, intense burst of cosmic creation, fusion effectively stopped. The universe continued its relentless expansion, and as it stretched further, temperatures dropped even more. For hundreds of thousands of years after this, the cosmos remained a hot, glowing plasma, a turbulent sea where electrons moved about freely, simply unable to settle into stable, long-lasting orbits around atomic nuclei. It was a universe of unattached particles. Light itself struggled to make any headway. Photons, the particles of light, were constantly bumping into and scattering off those free electrons, a process called Thomson scattering. Because of this constant interference, the universe was completely opaque, much more like the dense, glowing interior of a star than the vast, transparent space we effortlessly observe today. It was a cosmic fog, where light could not travel far before being scattered again. As the expansion persisted, the temperature eventually dipped below a critical threshold, reaching roughly 3,000 degrees Celsius. At that precise moment, the conditions were finally gentle enough for electrons to bind with nuclei without being immediately knocked away by energetic collisions. This allowed hydrogen and helium atoms to form in enormous numbers for the very first time. It was a moment of profound cosmic calm and organization, finally. This momentous event is known as recombination. Though, to be technically accurate, it was actually the first time these electrons combined with nuclei, rather than a recombination. With far fewer free electrons zipping around to scatter light, photons were finally able to travel freely through space, unimpeded. The universe, which had been a dense, glowing fog, suddenly became transparent. Light could now truly journey across the cosmos, carrying information. The very first light that was released at that pivotal moment still exists today, traveling across the vast stretches of time and space. Over billions of years, the continuous cosmic expansion has stretched its wavelength, shifting it from visible light all the way into the microwave range of the electromagnetic spectrum. We now detect this ancient glow as the cosmic microwave background, CMB, a faint, uniform radiation that subtly fills the entire sky, a pervasive echo of the early universe. If our eyes could somehow perceive microwave radiation, the night sky would never appear completely dark to us. Instead, it would softly glow in every single direction, a gentle luminescence that would carry a direct snapshot of the universe when it was just a tender 380,000 years old. It's like looking at a baby picture of the entire cosmos, a profound visual link to its infancy. Those tiny variations in temperature within that cosmic microwave background radiation correspond precisely to the slight density differences that were initially seeded during the period of cosmic inflation. These faint, almost imperceptible patterns are, in essence, the original blueprints for all the future cosmic structures. Every single galaxy we see today, from the smallest to the largest, can ultimately be traced back to those subtle, primordial fluctuations in the early universe. After the pivotal event of recombination, the universe settled into a long and surprisingly quiet era, often referred to as the cosmic dark ages. There were no stars yet, no galaxies shimmering and lighting up the vast expanse of the sky. The cosmos was filled predominantly with a diffuse, neutral hydrogen and helium gas, gently expanding into an ever-deepening darkness. It was a period of cosmic silence, a quiet waiting. Now, darkness, in this context doesn't imply emptiness or a complete lack of activity. The universe still possessed a subtle structure, defined by those faint density variations that had been imprinted much earlier. Regions that were infinitesimally denser than their surroundings exerted a slightly stronger gravitational pull. Over hundreds of millions of years, gravity, that patient and persistent force, began its slow, deliberate work of drawing matter together. Gravity, when compared to other fundamental forces like electromagnetism, is remarkably weak. Yet, it possesses one crucial advantage: it only attracts, never repels. Over truly immense stretches of time, even the most minute imbalance, the slightest accumulation of matter, can build up significantly. Gas clouds very slowly drifted toward those slightly denser regions, which, in turn, became even denser, gradually pulling in more and more material in a gentle, cascading effect. As these colossal clouds of hydrogen gas grew thicker and more massive, their central cores began to compress under their own immense weight. This compression naturally led to a rise in both temperature and pressure within the core. The entire process was agonizingly slow, but utterly relentless. The universe, which had once been so remarkably smooth and nearly uniform, was finally beginning to gather itself, to coalesce into the very first meaningful, large-scale structures. These nascent clouds were truly enormous, far, far larger than any individual star that would eventually form within them. They were, in essence, the ancestral nurseries of galaxies, vast reservoirs of gas that, as the collapse continued, would eventually fragment into smaller, denser regions. Each massive cloud held the potential for thousands, even millions, of future stars, a universe in miniature, slowly taking shape. Within the densest pockets of these collapsing clouds, gravity intensified the compression to an extreme degree, until temperatures in the core reached many millions of degrees. At that scorching temperature, hydrogen nuclei could finally overcome their natural mutual repulsion, their positive charges pushing each other away, and fuse together. For the very first time since the initial minutes of the universe, nuclear fusion, the engine of stars, made its grand return. And so, the very first stars flickered into existence, igniting in a universe that had been shrouded in darkness for hundreds of millions of years. Their brilliant light began to pierce through the surrounding hydrogen fog. These were not the gentle, long-lived stars like our Sun. On the contrary, these pioneer stars were incredibly massive, astonishingly luminous, and tragically, very short-lived, burning through their fuel at a furious pace. They were cosmic beacons, burning out quickly. Because the early universe contained almost no heavy elements, just hydrogen, helium, and a tiny bit of lithium, the gas within these collapsing clouds cooled much less efficiently. This particular condition allowed the first stars to accumulate truly enormous amounts of mass before they finally ignited their nuclear fusion. Some of these first stars may have been hundreds of times more massive than our Sun, blazing intensely and burning out in a cosmic flash. Deep inside the cores of these massive first stars, nuclear fusion began to forge elements heavier than helium for the very first time in the universe's history. Carbon, oxygen, and other crucial building blocks of life were created through these intense stellar furnaces. And when these titanic stars eventually met their explosive end, they scattered these newly synthesized elements out into the vast expanse of space, enriching the cosmos for future generations. The intense radiation emanating from these first stars also transformed the universe in another profound way. The high-energy light they emitted ionized the surrounding neutral hydrogen, stripping electrons once again from those newly formed atoms. The cosmos, which had settled into a neutral state, gradually began to shift back to an ionized state in a period known as reionization. It was like switching on a giant cosmic light bulb, changing the very nature of matter. Reionization didn't happen uniformly across the universe all at once. Instead, it spread outward from clusters of those early stars and galaxies, like islands of pure light gradually expanding into a dark, neutral sea. Over hundreds of millions of years, more and more regions became ignited by the stellar radiation, and the neutral hydrogen gas that filled the space between these nascent structures became increasingly transparent to light. It was a slow, majestic dawn for the cosmos. As light became able to travel more freely, the process of building large-scale structure in the universe became much easier. Gas continued to flow inward, guided along invisible, vast filaments largely shaped by dark matter. Dark matter, which doesn't emit or absorb light, exerts gravity, and it formed a vast, invisible cosmic web stretching across truly unimaginable distances. It was the scaffolding upon which everything else would be built. Dark matter had actually been present from the very beginning, interacting primarily through the force of gravity alone. While ordinary matter, the stuff we see and touch, scattered light and energy, dark matter quietly and unobtrusively formed gravitational scaffolding. Galaxies, in turn, would assemble and grow inside these massive, invisible halos of dark matter, drawn in by its dominant gravitational influence. It was the silent architect of the cosmos. Where these cosmic filaments intersected, ordinary matter accumulated most strongly, creating dense knots in the cosmic web. These highly concentrated regions became the birthplaces of the earliest galaxies. Within these nascent galaxies, gas continued to cool, fragmented into smaller clouds, and form generations of new stars, each contributing more heavy elements to the surrounding interstellar medium. It was a cycle of birth, death, and enrichment. Some of these early galaxies didn't just sit in isolation, they merged with one another, drawn together by the irresistible pull of gravity. These cosmic collisions dramatically reshaped them, often triggering intense waves of new star formation. Over vast stretches of cosmic time, smaller protogalaxies combined and accreted into much larger systems, gradually setting the stage for the elegant spiral and elliptical galaxies that we observe scattered across the universe today. At the very centers of many of these young, energetic galaxies, some of the most massive stars collapsed in on themselves, forming black holes. Some of these black holes then grew incredibly rapidly by accreting vast amounts of surrounding gas, eventually becoming millions of times more massive than our Sun. Their intense radiation and powerful jets created brilliant objects known as quasars, visible across billions of light-years, blazing with the energy of infalling matter. By about 1 billion years after the Big Bang, the universe was no longer dark, simple, or uniform. Galaxies of many shapes and sizes now filled space. Star formation was happening at a vigorous, frantic pace. The basic cosmic architecture, that vast web of matter, had firmly taken form, meticulously guided by the enduring force of gravity and initially seeded by those incredibly subtle quantum fluctuations from the inflationary epoch. It was a universe coming into its own. Yet, despite its rapidly growing complexity and brilliance, the universe was still very young. Most of the stars that would ever shine throughout cosmic history had not yet been born. Most galaxies had not yet fully assembled into their mature forms. Time, on these immense cosmic scales, was still very much in its early chapters, with billions of years of evolution still stretching out ahead. It was a universe of immense potential, still unfolding. If we pause here for a moment and look back at this incredible progression, the journey is absolutely striking. From a nearly uniform, featureless field of pure energy, intricate and complex structures somehow emerged. From tiny, almost imperceptible quantum fluctuations, entire galaxies, teeming with billions of stars, eventually arose. The universe, it turns out, didn't require some grand, predetermined blueprint in the traditional sense. If we pause here for a moment and look back at this incredible progression, the journey is absolutely striking. From a nearly uniform, featureless field of pure energy, intricate and complex structures somehow emerged. From tiny, almost imperceptible quantum fluctuations, entire galaxies, teeming with billions of stars, eventually arose. The universe, it turns out, didn't require some grand, predetermined blueprint in the traditional sense. The beginning, in this profound sense, is not something that abruptly ended, it is something that is still actively unfolding, constantly evolving around us. And somewhere within one unremarkable, average-looking spiral galaxy, far from its bright, bustling center, a future solar system will eventually begin to take shape. But that particular story lies many billions of years ahead from this precise moment in cosmic time. The beginning, in this profound sense, is not something that abruptly ended, it is something that is still actively unfolding, constantly evolving around us. And somewhere within one unremarkable, average-looking spiral galaxy, far from its bright, bustling center, a future solar system will eventually begin to take shape. But that particular story lies many billions of years ahead from this precise moment in cosmic time. The cosmic dark ages have finally drawn to a close. The first lights, those massive, brilliant stars, are now on, piercing the primordial darkness. Gravity has steadily begun its patient work, sculpting diffuse matter into distinct, luminous islands of stars. From this point forward, the long and intricate evolution of galaxies will continue, eventually giving rise to that quiet, unassuming corner of space that we now call our home, the Milky Way. When those first stars ignited, they didn't just shine, they permanently altered the very nature of the universe. Until that point, gravity had been silently, almost imperceptibly, shaping matter in the profound darkness. Now, light truly returned, not the fading, diffuse afterglow of the Big Bang, but concentrated, directional starlight, blazing through the expanding cosmos. It was a new kind of illumination, a focused energy that would drive further change. These pioneer stars are now known as population 3 stars. Unlike our Sun, which formed from gas-rich and heavier elements, these first stars formed from almost pure hydrogen and helium. With no heavier elements present to efficiently cool the collapsing gas clouds, they accumulated truly enormous amounts of mass before nuclear fusion finally stabilized them, making them titans among stars, burning with incredible ferocity. Because they were so utterly massive, their lifespans were incredibly brief, mere cosmic blinks. A star hundreds of times heavier than our Sun might only live for a few million years, which, on the grand timescale of the universe, is barely a moment. They burned with an almost unimaginable brightness, exhausting their nuclear fuel at an astonishing rate, destined for a swift and spectacular end. They were fireworks in the early cosmos. Deep inside their incredibly hot cores, temperatures climbed high enough to fuse not just hydrogen into helium, but to continue the nuclear chain reaction, helium into carbon, then carbon into oxygen, and onward towards even heavier elements. Each stage of this fusion process released enormous amounts of energy, temporarily balancing the crushing, inward pull of gravity, allowing the star to sustain its brilliant existence. But even stellar fusion has its limits. Once iron forms in the star's core, a critical point is reached. Further fusion reactions no longer produce energy, instead, they actually consume it. This fateful shift, rather than supporting the star against gravity, rapidly hastens its inevitable collapse. Gravity, which had been held at bay, suddenly wins its battle, compressing the core in an almost instantaneous fraction of a second, an irreversible implosion. This catastrophic core collapse triggers a supernova, one of the most energetic and violent events in the entire universe. In the incredible heat and pressure of that explosion, elements even heavier than iron are forged, including precious gold, dense uranium, and countless others, elements crucial for rocky planets and life. The star's outer layers are then blasted out into space at tremendous speeds, enriching the interstellar medium with these newly created elements. The powerful shock waves generated by these supernova explosions weren't just destructive, they also compressed nearby gas clouds, sometimes triggering the formation of new stars. In this profound way, one generation of stars actively seeded and stimulated the birth of the next. The universe was becoming chemically richer, more complex, with each passing cycle of stellar birth and death. It was a cosmic recycling program, forging new from old. Not all massive stars, however, met their end in the same dramatic way. Some of them collapsed into incredibly dense neutron stars, objects so compact that a single teaspoon of their matter would weigh billions of tons. Others collapsed even further, beyond the point where even neutrons could resist gravity, forming the ultimate cosmic voids, black holes, points of infinite density from which nothing, not even light, can escape. The black holes formed in this early era were not merely dead remnants, they were the seeds of something much, much larger. As they steadily pulled in surrounding gas and dust, their mass grew. In the dense, chaotic centers of nascent galaxies, some of them would eventually become supermassive black holes, millions or even billions of times the mass of the Sun, anchoring entire galaxies and influencing their evolution. While individual stars lived and died in their fleeting cosmic dance, galaxies themselves were undergoing a much grander assembly process. Small protogalaxies merged under the relentless pull of gravity, gradually forming larger and more complex systems. Each merger dramatically reshaped the orbits of existing stars, redistributed vast quantities of gas, and often triggered new, intense waves of star formation, revitalizing the galactic landscape. As these protogalaxies merged, their shapes were anything but orderly. Many were irregular, turbulent systems, seething with intense radiation and violent bursts of star formation. Over immense stretches of time, gravity slowly began to smooth out some of that chaos, allowing more stable, organized structures to emerge from the turbulent cosmic maelstrom. It was a gradual imposition of order from initial disorder. Spiral galaxies, with their elegant, sweeping arms, likely formed when gas clouds retained enough angular momentum during their collapse to flatten into rapidly rotating disks. Within these disks, new stars formed, tracing out those beautiful spiral arms, which are essentially density waves moving through the galactic plane, compressing gas and triggering stellar birth. They are majestic cosmic pinwheels, constantly evolving. Elliptical galaxies, by contrast, often resulted from major mergers, violent, head-on collisions between two similarly sized galaxies. When such a collision occurred, the orderly, rotating motion of the gas and stars could be completely disrupted, leaving behind a more rounded, three-dimensional swarm of stars orbiting the galactic center in many different directions, rather than in a flat plane. They are the cosmic footballs, often ancient and serene. Elliptical galaxies, by contrast, often resulted from major mergers, violent, head-on collisions between two similarly sized galaxies. When such a collision occurred, the orderly, rotating motion of the gas and stars could be completely disrupted, leaving behind a more rounded, three-dimensional swarm of stars orbiting the galactic center in many different directions, rather than in a flat plane. They are the cosmic footballs, often ancient and serene. Dark matter also offers an elegant explanation for a puzzling observation. Stars at the outer edges of galaxies orbit faster than our calculations suggest they should, based solely on the visible mass. Measurements consistently show that the visible matter alone cannot account for their speed. An unseen, vast halo of dark matter provides the essential extra gravitational pull needed to keep galaxies intact and prevent them from spinning themselves apart. As galaxies matured, their central black holes continued their steady growth. Gas spiraling inward toward these supermassive black holes formed intensely bright accretion disks, glowing across the electromagnetic spectrum. In some spectacular cases, powerful jets of particles were shot outward from the poles of these black holes at nearly the speed of light, blasting through the surrounding galaxy and beyond, profoundly influencing their surroundings. These incredibly energetic outflows from central black holes had a significant influence on their host galaxies. By heating and expelling vast amounts of gas, they could effectively regulate star formation, preventing galaxies from converting all their available material into stars at once. Even black holes, those ultimate devourers, played a crucial, albeit surprising, role in shaping the cosmic balance and the evolution of galaxies. Meanwhile, on scales far, far larger than individual galaxies, the vast cosmic web continued its intricate evolution. Those cosmic filaments acted like highways, funneling gas and galaxies inward, feeding immense galaxy clusters that contained hundreds or even thousands of galaxies, all bound together by the collective force of gravity. These clusters represent the largest known structures in the universe, true cosmic cities. Within these dense galaxy clusters, galaxies interacted frequently and sometimes violently. Some were stripped of their gas as they moved through the hot, diffuse intergalactic plasma, effectively starving them of new star-forming material. Others collided directly and merged. Over billions of years, these dynamic interactions shaped the incredible diversity of galaxies, with all their myriad forms, that we observe today. It was a cosmic ballet of destruction and creation. By roughly 3 billion years after the Big Bang, the universe had entered a period of peak star formation. Galaxies were churning out new stars at rates far higher than they do now, almost frantically. The cosmos was brighter, more active, and incredibly dynamic, filled with the vibrant glow of countless young, blue stars. It was a period of cosmic exuberance, a golden age for stellar birth. After this energetic peak, however, star formation began a slow, gradual decline. Galaxies, having spent billions of years furiously creating new stars, gradually consumed much of their available cold gas, the essential raw ingredient for making new stars. Without steady supplies of fresh material, stellar nurseries became less frequent and less intense. The universe didn't dim abruptly, but it began a subtle, gentle transition toward maturity, a more measured pace of stellar creation. It was during this long era of galactic growth and merger, this prolonged cosmic adolescence, that our own galaxy, the Milky Way, began to truly take shape. The Milky Way didn't just appear all at once, fully formed. Instead, it assembled itself piece by piece, slowly absorbing smaller galaxies and integrating their stars, gas, and dark matter into its steadily expanding and evolving structure. It was a cosmic accretion. Some of those ancient mergers are still faintly visible to us today. Streams of stars, like ghostly remnants, arc around the Milky Way, silent witnesses to smaller galaxies that were torn apart by the immense tidal forces of our own galaxy's gravity. They are faint, delicate signatures of a dynamic, often violent past, written across the vast canvas of our night sky, cosmic echoes of ancient encounters. At the very heart of the Milky Way lies a supermassive black hole, known by the prosaic name Sagittarius A star. It contains an astonishing mass, roughly 4 million times that of our Sun. Though it is currently in a relatively quiet state, it occasionally flares brightly as it consumes stray gas clouds or unlucky stars that wander too close to its immense gravitational maw, giving us glimpses of its awesome power. The Milky Way's iconic spiral arms are not rigid, unchanging structures. Rather, they are regions of higher density. Think of them like cosmic traffic jams, that move like waves through the galactic disk. As gas and dust pass through these denser regions, they get compressed, triggering the formation of new stars, which briefly illuminate the arms in the brilliant blue light of hot, young stars, making the spiral pattern visible. Our own solar system resides in one of the Milky Way's minor spiral arms, known as the Orion Arm, nestled comfortably far from the crowded, bustling central bulge. Here, stellar densities are lower, and catastrophic encounters between stars are blessedly rare. It is, in many important ways, a relatively calm and peaceful neighborhood within the vast, dynamic expanse of our galaxy. Stars, including our Sun, orbit the center of the galaxy in long, sweeping arcs that take hundreds of millions of years to complete. Since its formation, the Sun has circled the Milky Way many times over, each grand orbit unfolding with stately slowness compared to the brief span of human history. It's a journey that puts our human timelines into humbling perspective. By the time the universe was approximately 9 billion years old, the conditions in this quiet spiral arm of the Milky Way had become just right, allowing a cold, molecular cloud to begin its slow, majestic collapse. That cloud, now richly enriched by countless earlier supernovae, contained all the necessary elements, the cosmic stardust, for the formation of rocky planets and, eventually, the intricate chemistry that would lead to life. The long and intricate cosmic story that began with the tiniest quantum fluctuations and a primordial plasma was now preparing to produce something far more intricate and profound. Inside that slowly collapsing cloud lay the raw ingredients for a brand new star, a small but dynamic planetary system, and a future world that would one day gaze up at the heavens and ponder the profound question of how it all began. The molecular cloud that was destined to become our solar system was truly cold and incredibly vast, stretching across light-years of space. While it was mostly composed of hydrogen and helium, it also held significant amounts of carbon, oxygen, silicon, iron, and other heavier elements, all forged in the hearts and explosions of earlier generations of stars. It was a quiet place, but not perfectly still. It hummed with potential. Something, we're not entirely sure what, disturbed its delicate balance. Perhaps a nearby supernova sent a powerful shockwave rippling through the cloud. This wave compressed a portion of the gas, increasing its density just enough for gravity to finally take over and begin its slow, inexorable work. The collapse began, slowly at first, almost imperceptibly, setting in motion a chain of events that would lead to our home. As the cloud continued to contract under its own gravity, it began to spin faster, much like an ice skater pulling in her arms to increase her rotation, a process known as the conservation of angular momentum. This increasing rotation caused the material to flatten into a vast, swirling disk, with the vast majority of the mass gathering steadily toward the very center. That central region grew progressively hotter and denser over time. In the very middle of this rapidly spinning disk, the pressure steadily increased to immense levels. When temperatures at the core reached an astonishing 10 million degrees Celsius, hydrogen nuclei finally began to fuse together, combining to form helium. A brand new star ignited. The Sun switched on, not with a sudden, visible explosion, but with a sustained and steady release of nuclear fusion energy, bathing its nascent system in light. Around the newborn Sun, the remaining disk of gas and dust continued its slow, graceful rotation. Tiny dust grains, microscopic fragments of the cloud, collided gently at first, sticking together through weak electrostatic forces. Over thousands of years, these minute grains slowly accumulated, forming pebbles, then rocks, then ever larger clumps. It was a gradual process of accretion, building from the smallest components. As these clumps grew larger, gravity began to play a more significant role, actively assisting the process. Kilometer-sized bodies, now known as planetesimals, formed and began to collide. Some of these collisions were destructive, shattering the bodies, while others merged them into even larger masses. The early solar system was an intensely chaotic and violent place, a cosmic demolition derby of building blocks. Closer to the blazing sun, temperatures were incredibly high, allowing only metals and silicates, rocky materials, to solidify and condense out of the gas. Farther out, in the colder reaches of the disk, it was chilly enough for ices, like water, methane, and ammonia, to form. This fundamental temperature gradient across the protoplanetary disk explains why the inner planets became dense, rocky worlds, while the outer planets grew into the massive gas and ice giants we see today. Jupiter, the largest planet, likely formed very early and remarkably quickly, accumulating an enormous mass before the surrounding disk of gas and dust completely dispersed. Its immense gravity profoundly influenced the orbits of smaller bodies throughout the solar system, shaping its overall architecture and perhaps even protecting the inner planets from some of the more devastating impacts by deflecting comets and asteroids. Meanwhile, in the inner disk, several protoplanets, embryonic planets, competed fiercely for the available material. Through repeated, often violent collisions and mergers, four distinct rocky worlds gradually emerged: Mercury, Venus, Earth, and Mars. Their surfaces, in these early stages, were molten, constantly being reshaped and scarred by the ceaseless barrage of impacts from leftover debris. It was a world of fire and impact. One of these developing worlds, the young Earth, was still very much in the process of assembling itself. Heavy elements, particularly iron, sank inexorably toward its center, forming a dense, metallic core. Lighter materials, such as silicates, floated upward, eventually creating a distinct mantle and a thin crust. This process, known as differentiation, gave Earth its characteristic layered internal structure, a separation of elements by density. Not long after Earth had solidified into a distinct planet, another protoplanet, roughly the size of Mars, crossed its orbital path. This body is often referred to by scientists as Theia. Its orbit eventually became unstable, and, in a glancing but utterly catastrophic impact, it collided with the young Earth. It was an event of unimaginable violence and transformative power, forever altering our planet. The collision released an unimaginable amount of energy, far beyond anything we can truly comprehend. Rock vaporized instantly. Vast oceans of molten magma surged across the surface of the scarred planet. An enormous plume of superheated debris was blasted into orbit around Earth, forming a glowing, fiery ring of molten fragments that majestically circled the wounded planet, a temporary crown of destruction. Over time, the relentless force of gravity slowly pulled that orbiting debris together. Collisions within the fiery ring caused the fragments to merge, gradually forming a single, large body. Within a few tens of millions of years, a blink in cosmic time, our moon, Earth's faithful companion, had taken shape, born from the violence of a planetary collision, a child of impact. At first, the newly formed moon orbited much, much closer to Earth than it does today. It would have appeared as an enormous, dominant presence in the sky, exerting incredibly powerful tidal forces on the planet's still molten surface and, later, on its forming oceans. Its proximity would have caused colossal tides, shaping the very crust of the young Earth, slowing its rotation. At first, the newly formed moon orbited much, much closer to Earth than it does today. It would have appeared as an enormous, dominant presence in the sky, exerting incredibly powerful tidal forces on the planet's still molten surface and, later, on its forming oceans. Its proximity would have caused colossal tides, shaping the very crust of the young Earth, slowing its rotation. In the immediate aftermath of that titanic impact, Earth remained incredibly hot, a world of fire. Its entire surface was likely covered by a global magma ocean, a swirling sea of molten rock. Gradually, as this intense heat radiated away into the coldness of space, the outermost layer began to cool and solidify, slowly forming the earliest, fragile crust of our planet. It was a gradual, agonizing process of cooling. Volcanic activity during this period was intense and ceaseless, erupting violently across the young planet. Gases trapped deep inside the planet's interior escaped furiously through these eruptions, building a thick, early atmosphere. This atmosphere contained vast amounts of water vapor, carbon dioxide, nitrogen, and trace amounts of other gases, but crucially, almost no free oxygen, a very different sky from what we know. As the planet continued to cool further, the immense amounts of water vapor suspended in the atmosphere began to condense. Rain, probably torrential and continuous, fell onto the still hot rock, instantly boiling and rising again, only to fall once more in an endless cycle. This hydrological cycle continued for thousands of years, gradually filling the planet's lowest basins with liquid water, shaping the early continents. Eventually, stable, vast oceans formed. The surface of Earth slowly transformed from a glowing, fiery red to a deep, shimmering blue. Beneath dark, perpetually cloud-filled skies, immense waves rolled across a young planet that had only recently survived violent impacts and colossal cosmic collisions. It was a world being reborn, a blue marble emerging from chaos, ready for its next chapter. The stage was now perfectly set for a dramatically different kind of transformation. The universe, in its grand, patient unfolding, had produced stars and galaxies, and our Earth had formed from their scattered, enriched remnants. Now, within its warm, mineral-rich oceans and its nascent crust, chemistry itself would begin to explore entirely new and unforeseen possibilities, building ever more intricate structures. The early Earth was anything but calm in the way we perceive calmness today. Volcanoes erupted almost constantly, lightning flashed relentlessly through thick, dense clouds, and the young oceans were rich with dissolved minerals, a potent chemical soup. Yet, in this restless, dynamic environment, chemistry had a critical combination of time, energy, and raw material to endlessly experiment and combine. Simple molecules, such as water, carbon dioxide, methane, ammonia, and nitrogen, were all present in varying, abundant amounts. With heat surging from volcanic vents, energy sparking from lightning strikes, and radiation pouring in from the sun, these molecules continuously collided, broke apart, and recombined in countless, intricate ways, exploring a vast landscape of chemical possibilities, constantly building and breaking. Scientists still engage in spirited debate about the exact setting in which life first began. One compelling possibility points to the warm, shallow ponds envisioned by Charles Darwin, acting as little cradles of life. Another, perhaps even more intriguing hypothesis, focuses on deep-sea hydrothermal vents, where superheated, mineral-rich fluids rise from cracks in the ocean floor, creating unique chemical microenvironments. Hydrothermal vents are particularly intriguing because they naturally provide crucial chemical gradients, metal-rich surfaces that can act as catalysts, and a steady, reliable source of energy in the form of chemical reactions. In these dark, isolated underwater environments, molecules could have assembled into increasingly complex forms, crucially protected from the harsh, damaging ultraviolet radiation that bombarded the surface. At some point, chemistry crossed a truly remarkable and profound threshold. Certain molecules acquired the astonishing ability to make imperfect copies of themselves. Once this crucial process of self-replication began, the relentless engine of natural selection could immediately begin to act, even before true, membrane-bound cells had fully come into existence. The universe had, almost by chance, stumbled onto a brand new kind of persistence, biological inheritance. Eventually, simple, fragile membranes formed, creating tiny, enclosed compartments that crucially separated the internal chemistry from the external environment. These rudimentary protocells were not yet fully alive in the sophisticated sense we understand today, but they represented an incredibly important, foundational step toward life as we know it, creating the first sense of an inside and outside. By approximately 3.8 billion years ago, the earliest true cells may already have existed. They were likely very simple organisms, lacking a distinct nucleus or other complex internal compartments, resembling modern bacteria or archaea in their basic structure. Their world was entirely microscopic, but their importance, as the progenitors of all life, was absolutely immense and foundational. These very first organisms did not breathe oxygen, for the simple reason that there was almost none in the atmosphere. Instead, they relied on a variety of ingenious chemical reactions involving substances like iron, sulfur, hydrogen, or methane to fuel their metabolism. Earth's early biosphere was a truly strange and alien place compared with the oxygen-rich world we inhabit today, a testament to life's adaptability. For a very, very long time, life remained remarkably simple and microscopic. If you could somehow visit Earth during this vast era, you might observe immense oceans and active volcanoes, but you would see no lush forests, no darting fish, no soaring birds, and absolutely no visible sign from a distance that the planet was teeming with inhabitants. Life was present, but it was hidden, a silent, microscopic world. Yet, beneath that seemingly empty surface, the relentless process of evolution was already hard at work, slowly but inexorably shaping the future. Tiny variations between individual organisms determined which ones were better equipped to survive and reproduce. Over millions upon millions of generations, those subtle variations accumulated, slowly but surely shaping the first, fundamental branches of life's intricate tree. Some of the earliest microbial communities formed fascinating layered structures known as stromatolites. These were essentially built by colonies of microorganisms trapping sediment and slowly growing upward, inching toward the sunlight. Fossilized stromatolites, remarkably preserved in ancient rocks, remain among the oldest visible records of life's presence on Earth, enduring monuments to primeval life. For well over 1 billion years, bacteria dominated the planet, an unseen empire of microbes. They spread tirelessly through the vast oceans, colonized coastlines, and even thrived beneath the surface of rocks, adapting to almost every conceivable niche. Life was omnipresent, but it remained subtle and small, utterly invisible to any casual observer standing on the shore, a hidden, thriving world. Among these ubiquitous microorganisms, a truly remarkable and revolutionary innovation suddenly appeared: photosynthesis. Certain bacteria developed the astonishing ability to harness sunlight to power their metabolism, converting simple carbon dioxide and water into complex organic molecules, their own food. In this transformative process, they released oxygen as a crucial byproduct, slowly changing the planet's atmosphere. At first, the newly produced oxygen didn't immediately accumulate in the air. Instead, it reacted quickly and efficiently with the abundant dissolved iron in the oceans, forming iron oxides that slowly settled to the seafloor. These massive chemical reactions created the vast, distinctive banded iron formations that geologists still meticulously study today, tangible records of Earth's ancient, oxygen-starved past. Eventually, the oceans became utterly saturated with oxygen. There was no more dissolved iron left to react with. With nowhere else to go, oxygen began to escape into the atmosphere. Around 2.4 billion years ago, atmospheric oxygen levels rose significantly and dramatically in what we now call the Great Oxidation Event. The entire chemistry of the planet shifted profoundly and irreversibly. For many existing anaerobic organisms, oxygen was not life-giving, but a deadly toxin. Entire lineages of life declined dramatically or retreated into specific environments where oxygen remained scarce, finding refuge in oxygen-free pockets. It was one of the planet's first great biological crises, a mass extinction of microbial life, though it unfolded slowly over millions of years rather than days or weeks. Yet, oxygen also presented an extraordinary opportunity. Some organisms, through the relentless process of natural selection, evolved ingenious ways to use oxygen for respiration, a far more efficient process for extracting energy from nutrients than anaerobic metabolism allowed. This immense energetic advantage paved the way for the development of much greater biological complexity, pushing life to new levels of organization. Inside certain cells, a profound and enduring partnership formed. One cell, perhaps a larger host, engulfed another smaller cell but, crucially, did not digest it. Instead, the smaller cell continued to produce energy inside its host. Over vast stretches of time, this symbiotic relationship became permanent and indispensable, giving rise to mitochondria, the powerhouses of more complex cells. These new, more complex cells are known as eukaryotes. They contained intricate internal compartments, including a distinct nucleus to house their precious genetic material. Compared to the simpler bacteria, eukaryotes were significantly larger, far more flexible, and, most importantly, capable of organizing themselves in entirely new and sophisticated ways, opening the door to multicellularity and diversification. For hundreds of millions of years, even after their appearance, eukaryotic life remained primarily single-celled, a hidden world of microscopic complexity. But the essential groundwork for multicellularity, for organisms made of many cells, had now been firmly laid. These cells had abundant energy, sophisticated internal structures, and the inherent ability to cooperate. The next great leap would involve working together, rather than living alone. Earth did not remain consistently warm and hospitable during this long microbial era. Several times, the planet may have plunged into extreme glacial periods, so severe that they are known as snowball Earth events. Ice sheets could have covered much of the surface, possibly reaching even equatorial regions, turning the entire planet into a giant, frozen sphere, an alien landscape. If the oceans were indeed sealed beneath unimaginably thick ice, life somehow managed to survive in various refuges, perhaps near those deep-sea hydrothermal vents, beneath thinner ice in volcanically active areas, or in isolated pockets of liquid water maintained by geothermal heat. Even global freezing, it seems, was not enough to extinguish life completely. It proved remarkably resilient, clinging on in extreme conditions. Eventually, relentless volcanic activity released enough carbon dioxide into the atmosphere to warm the planet again, slowly but surely. The vast ice sheets retreated, the oceans reopened to life-giving sunlight, and essential chemical cycles resumed. These dramatic climate swings may have acted as powerful evolutionary pressures, forcing life to adapt in new and incredibly creative ways, accelerating diversification. Around 600 million years ago, a truly transformative shift occurred. Multicellular organisms became much more widespread and apparent. Cells began to specialize, forming distinct tissues with different, dedicated functions. Instead of every cell performing every task, groups of cells now cooperated harmoniously within larger, more complex bodies, leading to an explosion of biological forms. In the late Precambrian seas, strange, soft-bodied creatures began to appear. Some of them resembled quilted discs, while others looked like delicate fronds anchored to the seafloor. These enigmatic ediacaran organisms looked distinctly unlike most modern animals, representing an early, bold experiment in complex life, a tentative step beyond the microbial world. They were an evolutionary dead end in many ways, but a crucial step. Then, about 541 million years ago, the fossil record suddenly shows an astonishing increase in biodiversity, an event famously known as the Cambrian explosion. Within a relatively short geological period, many of the major animal body plans that we recognize today rapidly emerged. Life's evolutionary pace, which had been so slow and gradual for billions of years, seemed to accelerate dramatically, bursting forth with new forms. One key innovation during this period was the evolution of hard parts, such as protective shells and rigid exoskeletons. These provided crucial protection against predators and structural support, allowing organisms to grow larger and move more efficiently. Importantly, they also fossilized much more readily, giving us a clearer, richer evidence of this extraordinary evolutionary burst, a window into ancient diversification. Eyes, those complex organs of vision, evolved independently in multiple different lineages during the Cambrian period. With the advent of vision came entirely new ecological dynamics. Predators could now detect prey from a distance, and prey, in turn, evolved elaborate defenses and escape mechanisms in response. An evolutionary arms race, fueled by seeing and being seen, unfolded in the ancient oceans, driving further change. The basic architectural plans of many modern animal groups can be directly traced back to this period. Arthropods, like crabs and insects, mollusks, like snails and squid, and chordates, the lineage that would eventually include fish, amphibians, reptiles, mammals, and ultimately humans, all have their evolutionary roots deeply embedded in the bustling, dynamic Cambrian seas. It was a foundational moment for animal life. Life, which had once been limited to microscopic simplicity, now literally swam, crawled, burrowed, and hunted. The vast oceans were no longer dominated solely by microbes. They had transformed into vibrant, complex ecosystems, teeming with movement, interaction, and competition, a bustling, watery world filled with novel forms and behaviors, a far cry from the quiet microbial mats. For a very long time, life remained strictly confined to the oceans, a watery existence. But then, roughly 470 million years ago, plants began their tentative, brave journey, edging toward the land. At first, they were small and simple, hugging moist shorelines where water was always close at hand, never venturing far from their aquatic roots, dependent on the wetness for survival. Over millions of years, plants evolved crucial vascular systems, internal plumbing to transport water and nutrients throughout their bodies. This revolutionary innovation allowed them to grow much taller, competing for sunlight. Roots anchored them firmly into the soil, which they themselves helped create by slowly breaking down rock. Slowly but surely, the barren continents began their majestic transformation, turning green, terraforming the planet. Insects followed closely behind, becoming some of the very first animals to truly thrive on land, adapting to the terrestrial environment. During the Carboniferous period, atmospheric oxygen levels were significantly higher than they are today. That extra oxygen allowed insects to grow to truly enormous sizes. Some ancient dragonflies had wingspans well over 2 feet wide, a truly awe-inspiring sight. Meanwhile, fish living in shallow waters began to develop stronger, more robust fins and primitive lungs, adapting to environments with fluctuating water levels and oxygen availability. Around 370 million years ago, some of these brave fish ventured out of the water and onto land. These early amphibians still depended on water for reproduction, but they opened an entirely new frontier for vertebrate life, a colossal step in evolution. Reptiles evolved later, with a truly crucial innovation, the amniotic egg. Unlike the vulnerable amphibian eggs, which had to remain in open water to survive, the amniotic egg contained its own internal water supply and protective membranes. This revolutionary adaptation freed reptiles from their dependence on ponds and rivers, allowing them to spread across much drier, more diverse environments, colonizing new landscapes. About 252 million years ago, Earth experienced the most devastating extinction event in its entire history, the Permian mass extinction, often called the Great Dying. Massive volcanic eruptions in what is now Siberia released colossal amounts of greenhouse gases, profoundly altering the climate and the chemistry of the oceans. Roughly 90% of all marine species, and 70% of terrestrial vertebrate species, simply disappeared. From the ashes of this near-total collapse, new groups of life gradually emerged. Among them were the early dinosaurs. At first, they were relatively small, lightly built animals, often walking upright on 2 legs. Their unique posture gave them an efficient stride and, crucially, better breathing capacity than many of their sprawling competitors, a subtle advantage that would later prove pivotal. Dinosaurs did not immediately dominate the planet. For millions of years, they lived alongside a variety of other reptiles and early mammals. But gradual climate shifts and another extinction event around 201 million years ago, the Triassic-Jurassic extinction, cleared out many of their rivals. With less competition, dinosaurs diversified rapidly afterward, expanding into a vast array of ecological niches. Some dinosaurs grew to become true giants, creatures of staggering proportions. Argentinosaurus, for example, may have reached lengths of over 30 meters, nearly 100 feet, and weighed as much as 15 elephants. To pump blood all the way up its incredibly long neck, its heart may have been the size of a small car, an enormous organ to sustain its immense body. Predators evolved just as impressively, becoming terrifyingly efficient. Tyrannosaurus rex possessed teeth as long as bananas and a bite force stronger than any other land animal known to science. Yet, even T-Rex likely had feathers, at least in its youth, a detail that reminds us that dinosaurs were far more diverse and complex than the scaly monsters often depicted in popular culture, often resembling giant birds. Many dinosaurs were far more dynamic and active than early museum skeletons suggested. Extensive fossil evidence now shows that some species lived in herds, moving together across vast floodplains, much like modern-day wildebeest. Trackways preserved in ancient rock reveal coordinated motion, almost like snapshots of ancient migrations, offering tantalizing glimpses into their complex social behaviors. Nests discovered in Mongolia and North America reveal that certain dinosaurs cared for their young, exhibiting parental behaviors. Eggs were arranged carefully, and some rare fossils even preserve adult dinosaurs positioned protectively over their nests, guarding their offspring. Parenthood, it seems, did not begin with mammals. It has deep evolutionary roots extending far back into the age of reptiles. One particular small dinosaur, called Troodon, possessed a relatively large brain for its body size, suggesting a higher degree of intelligence than many of its contemporaries. While certainly not intelligent, in a human sense, it indicates that some dinosaurs likely possessed sharper senses and more complex behaviors than we once imagined, overturning old stereotypes of lumbering dim-witted giants. Feathers, once thought to be exclusive to birds, have now been found in numerous non-avian dinosaur fossils. It's likely that some feathers evolved first for insulation, keeping the dinosaurs warm, or for display, attracting mates, rather than for flight. Only much later did certain lineages adapt them for powered flight, paving the way for the evolution of birds. In a profound evolutionary twist, birds are, in fact, living dinosaurs. Every sparrow chirping outside your window, every majestic eagle soaring overhead, and every waddling penguin carries forward a direct lineage that miraculously survived when all other major dinosaur branches ended. The age of dinosaurs, in this sense, never truly disappeared, it simply changed form, taking to the skies. For over 160 million years, dinosaurs dominated terrestrial ecosystems, reigning supreme across the globe. During that immense span of time, continents slowly drifted apart, climates shifted dramatically, and flowering plants evolved, fundamentally changing landscapes. Entire mountain ranges rose and eroded while dinosaurs continued their diverse existence, a testament to their incredible evolutionary success. Then, 66 million years ago, an event of cosmic significance occurred. A 6-mile-wide asteroid, traveling at immense speed, struck the Earth near present-day Mexico. The impact released more energy than billions of atomic bombs combined. Shockwaves reverberated around the entire planet, and vast quantities of superheated debris were blasted high into the atmosphere, initiating a global catastrophe. Massive fires ignited across continents as ejecta rained back down to Earth. Dust and aerosols injected high into the atmosphere blocked out sunlight for months, possibly even years, plunging the planet into a prolonged period of darkness and chilling cold. Photosynthesis faltered, collapsing food chains from the bottom up. Within a relatively short geological period, about 75% of all species on Earth vanished. Every single non-avian dinosaur disappeared, wiped out by the cataclysm. The colossal giants that had ruled for millions of years were gone, their reign abruptly ended. Yet, small feathered descendants, birds, survived, along with many mammals, reptiles, and countless microscopic organisms. Extinction, though devastating, cleared vast ecological space for new forms of life to emerge and diversify. With the mighty reptiles gone, mammals, which had largely lived in the shadows for millions of years, mostly small and nocturnal, began rapidly expanding into new ecological niches. The world was quieter in some ways, certainly without the roar of a T-Rex, but evolution was far from finished. The next grand chapter would unfold slowly, leading eventually to forests filled with diverse mammals and, much, much later, to us. After the extinction event that marked the end of the age of dinosaurs, mammals began to diversify with astonishing speed. For millions of years, they had existed as relatively small, unassuming creatures, often nocturnal, occupying marginal niches. Now, with the dominant dinosaurs gone, ecosystems were wide open, and evolution moved quickly to fill the vast array of empty roles and opportunities. Some mammals, against all odds, returned to the oceans, gradually evolving into the magnificent whales we know today. Their ancient ancestors once walked on land, but over vast stretches of time, their limbs transformed into powerful flippers, and their nostrils migrated upward on their heads to become blowholes, perfectly adapted for an aquatic existence. It was a remarkable journey back to the sea. Others took to the skies, evolving the power of flight. Bats, for instance, developed powered flight entirely independently of birds, using elongated fingers stretched by membranes to create their wings. They became undisputed masters of the night, navigating through the darkness using echolocation, emitting high-pitched sounds and sensing the world through the echoes that bounced back, creating a sonic map. On land, mammals grew larger and more diverse. Forests spread across warm continents, and new, distinct groups emerged: hoofed animals like deer and horses, a variety of carnivores like cats and dogs, and eventually, the primates. The planet was entering a new ecological balance, one defined less by the cold-blooded reptiles and more by the fur and warm blood of mammals, radiating into new forms. Primates evolved a specific set of traits that would later prove absolutely crucial for our own lineage: forward-facing eyes, providing excellent depth perception, essential for navigating complex arboreal environments, flexible hands for grasping branches with precision, and relatively large brains for processing complex sensory information and social interactions. Life in the trees rewarded coordination, awareness, and intelligence. Around 7 million years ago in Africa, one particular lineage of primates began spending more and more time on the ground. Significant climate shifts had reduced forest cover in some regions, expanding vast grasslands. Standing upright, on two legs, offered distinct advantages in this new, open environment, allowing for better visibility over tall grasses and freeing up the hands for other tasks. Bipedal walking, this fundamental shift, completely freed the hands. Hands could now carry food, tools, or infants more easily, providing a crucial evolutionary advantage. Over countless generations, subtle skeletal changes refined balance and stride. The spine curved differently, and the pelvis reshaped itself to efficiently support an upright posture, perfecting the mechanics of two-legged locomotion. By about 2 million years ago, members of the genus Homo, our direct ancestors, were already crafting simple stone tools. These tools were not symmetrical masterpieces, certainly, but they were remarkably effective at cutting meat from carcasses and cracking open bones to access nutritious marrow. Access to richer, protein-dense food, in turn, provided the vital energy needed to support the growth of larger, more complex brains. Fire followed, a transformative discovery. Whether it was first captured from natural wildfires or deliberately created through friction, controlled fire provided essential warmth, protection from predators, and, crucially, cooked food. Cooking made nutrients much easier to absorb, further supporting rapid brain growth. Evenings spent around firelight also likely changed social life profoundly, fostering community and storytelling. Over time, language became increasingly sophisticated and nuanced. With language came the unprecedented ability to share complex ideas, plan cooperative hunts with greater efficiency, and pass accumulated knowledge and skills across generations, building a cumulative culture. Culture, a uniquely human trait, began layering itself on top of biology, becoming the primary driver of our evolution. The asteroid impact, though causing immediate destruction, also had prolonged effects. Dust and sulfur particles injected high into the atmosphere reflected sunlight for months, possibly even years. Global temperatures dropped sharply, plunging the planet into an impact winter. Plants, starved of light, struggled to survive, and herbivores, lacking food, soon followed their decline. Acid rain may have also fallen across the globe, severely altering soil chemistry and freshwater systems, rendering them toxic. In the oceans, plankton populations plummeted, disrupting the base of marine food webs and sending shockwaves through aquatic ecosystems. The extinction, though swift geologically, unfolded in waves, affecting different ecosystems across the planet in varied and devastating ways. Small animals with flexible diets had a much better chance of survival in this chaotic environment. Creatures that could burrow underground, eat seeds, or remain dormant during the harshest periods endured when larger, more specialized creatures could not. Survival, in this new world, favored adaptability, resilience, and a smaller size over raw power or specialization. Birds, as the only surviving lineage of dinosaurs, carried forward a crucial part of that ancient heritage. Their small bodies, diverse diets, and the ability to fly, allowing them to escape local catastrophes and find new food sources, may have helped them persist. The skies did not fall silent, they simply changed their inhabitants, with birds filling the ecological void left by their larger dinosaur cousins. When sunlight gradually returned and climates slowly stabilized, ecosystems painstakingly rebuilt themselves from the surviving species. Forests regrew, new evolutionary experiments began, and the world after the extinction was certainly not empty, but it was profoundly reshaped, leading to a new era dominated by mammals and birds, a new chapter in the story of life on Earth. By around 300,000 years ago, Homo sapiens, our own species, had appeared in Africa. They were anatomically very similar to us, possessing high foreheads and complex vocal capabilities, indicative of sophisticated language. Yet, they were still one human species among several, sharing the planet with other hominin relatives, a world more diverse in human forms than today. Neanderthals, for instance, inhabited Europe and Western Asia, adapted to colder climates with sturdy builds and powerful physiques. Denisovans lived in parts of Asia, known primarily from genetic evidence. For thousands of years, these different human groups overlapped, sometimes competing for resources, sometimes interbreeding, exchanging genes and cultural practices. Genetic evidence today clearly shows that many people living now carry small percentages of Neanderthal or Denisovan DNA in their genomes. Human history, it turns out, is not a simple, straight line of progression, but a braided stream with multiple branches that occasionally rejoined, enriching the genetic tapestry of our species. We are a mosaic of ancient encounters. What most clearly distinguished Homo sapiens, however, was their capacity for truly symbolic thought. Elaborate cave paintings, intricately carved figurines, decorative beads, and sophisticated musical instruments all suggest minds capable of abstract imagination, complex storytelling, and shared belief systems, a deep inner world expressed through art and ritual. Around 70,000 years ago, groups of Homo sapiens began leaving Africa in larger numbers, initiating a grand global diaspora. They followed coastlines and river valleys, adapting to incredibly diverse environments, scorching deserts, dense forests, and eventually even icy northern climates. The human journey across the globe, a remarkable feat of endurance and adaptation, had truly begun. As humans spread across Eurasia and eventually beyond, they encountered environments unlike anything their ancestors had ever known. Dense, ancient forests, towering mountain ranges, vast, arid deserts, and frozen tundra all demanded new tools, new strategies, and new ways of life. Adaptation was no longer just biological, it was primarily cultural, a testament to human ingenuity. During the last Great Ice Age, immense parts of the northern continents were covered by massive, towering ice sheets, fundamentally reshaping landscapes. Sea levels were significantly lower, exposing land bridges that no longer exist today, such as Beringia between Asia and North America. These temporary pathways quietly, but profoundly, shaped the map of early human migration. One such crucial land bridge connected Siberia and North America. Groups of humans gradually crossed it, perhaps not even realizing they were stepping onto an entirely new continent. Over many thousands of years, their descendants would slowly spread throughout the Americas, adapting to an incredibly diverse array of ecosystems, leaving their genetic and cultural imprints. Hunter-gatherer life required incredibly detailed, intimate knowledge of local ecosystems. People tracked migrating herds, recognized edible plants, understood seasonal patterns of growth and availability, and possessed profound ecological wisdom. Survival depended on keen observation, an impressive memory, and strong cooperation within small, cohesive social groups, building a communal knowledge base. Communication became increasingly complex and nuanced. Stories were not just entertainment, they served as powerful vehicles to pass vital knowledge across generations, about dangerous animals, hidden water sources, or the profound meaning of the stars overhead. Language allowed humans to coordinate their actions and build social structures far beyond what instinct alone could ever manage, fostering cumulative learning. The night sky during the Ice Age would have appeared spectacularly clear and brilliant. With absolutely no artificial lights to diminish its splendor, the Milky Way would have stretched brightly overhead, a breathtaking river of stars. Ancient humans likely wove constellations into rich myths and legends, connecting earthly events with the unchanging, celestial patterns in the heavens, seeking meaning in the cosmic expanse. Around 12,000 years ago, a pivotal shift occurred. The climate warmed dramatically at the end of the last ice age. Massive glaciers retreated, sea levels rose, and ecosystems shifted once more, creating new opportunities. In several distinct regions across the globe, humans began to experiment with cultivating wild grains, actively planting and harvesting them, instead of simply gathering them as they found them. Agriculture emerged independently in multiple places around the world, in the Fertile Crescent of the Middle East, in China, in Mesoamerica, and elsewhere. It was not a single invention, but rather a pattern of innovation that was repeated wherever conditions allowed. Humans began to intentionally shape landscapes and ecosystems to produce food, marking a profound shift in their relationship with nature. Settled life, brought by agriculture, fundamentally changed social structures. Permanent villages formed, populations grew significantly, and food surpluses supported the emergence of specialization. Some people farmed, others crafted tools, while others managed trade or defended the community. Social complexity increased gradually, generation by generation, building ever more intricate societies. With permanent settlements came entirely new challenges. Disease spread more easily in crowded conditions, social hierarchies formed, and conflicts over land and resources intensified. Yet, cities also became vibrant centers of innovation, where ideas could accumulate, be shared, and expand, leading to rapid advancements in technology, art, and governance, driving human progress. In Mesopotamia, the fertile land between the Tigris and Euphrates rivers, early cities rose from rich floodplains. Elaborate irrigation canals redirected water into fields, transforming unpredictable seasonal floods into reliable, predictable harvests. Agriculture there became organized on an unprecedented scale, supporting large urban populations and complex societal structures, giving birth to civilization. As harvests grew, so too did the crucial need to keep accurate records of grain, livestock, and transactions. Clay tablets pressed with wedge-shaped marks became one of the earliest writing systems, cuneiform. At first, it meticulously tracked grain and trade, but soon it carried stories, laws, and prayers, becoming a powerful tool for knowledge transmission and governance. In ancient Egypt, the Nile River's annual, predictable flooding deposited rich, fertile silt along its banks, replenishing the soil. This reliable rhythm supported a stable, unified kingdom for centuries. Massive pyramids were constructed with astonishing precision, aligned closely with cardinal directions and celestial patterns, enduring testaments to their advanced engineering and astronomical knowledge. Far to the east, along the Yellow River, early Chinese dynasties developed sophisticated bronze metallurgy and complex bureaucracies to govern their growing empires. Writing systems emerged independently there, demonstrating that human innovation does not follow a single geographic path, but arises from diverse cultural and environmental contexts, a testament to universal human ingenuity. In the Indus Valley, cities such as Mohenjo-Daro were remarkably laid out on grid patterns, boasting advanced drainage systems and public baths. Streets were carefully planned, bricks standardized, and water managed with impressive foresight. Urban planning, it seems, appeared remarkably early in human history, reflecting sophisticated social organization and centralized authority. Trade connected distant cultures, weaving a vast web of interaction. Lapis lazuli from Afghanistan, tin from Central Asia, exotic spices from India, goods moved across truly vast distances. Along with objects traveled ideas, technologies, and beliefs, enriching and transforming societies. Civilization was becoming increasingly interconnected, a global exchange of goods and ideas. Empires formed to control vast resources and territories, bringing diverse peoples under a single rule. The mighty Persian Empire stretched across 3 continents, from Africa to Asia. Later, Rome built roads so durable and well-engineered that some remain visible and in use today. This sophisticated infrastructure allowed ideas and authority to move efficiently across large, complex populations, facilitating control and integration. Ancient Greece introduced profound philosophical traditions that emphasized logic, reason, and rigorous inquiry. Thinkers like Aristotle and Plato asked fundamental questions not only about the natural world but also about ethics, politics, and the very nature of knowledge itself. Curiosity became formalized into structured thought, laying the foundations for Western philosophy and science. In China, Confucian and Taoist philosophies deeply shaped governance, social ethics, and daily life, providing moral and spiritual frameworks. In India, early Hindu and Buddhist traditions explored profound questions of consciousness, suffering, and enlightenment. Across continents, humans were striving to understand their place in the cosmos, seeking meaning in the vastness. Despite these regional differences and grand developments, most people still lived relatively simple lives as farmers, tied to the land. They rose with the sun, worked the soil, and slept under familiar constellations, their lives dictated by the seasons. Above them, the stars appeared largely unchanged, steady, silent witnesses to the ceaseless march of human change unfolding below, a constant in a world of flux. Life in ancient cities, however, was not only about grand monuments and powerful kings. It smelled distinctively of wood smoke, livestock, freshly baked bread, and the ever-present river mud. Markets were loud, crowded, and vibrant places where many languages mixed, and news traveled faster than any official messenger could carry it, a bustling hub of human activity and exchange. It turned out that water truly held the keys to everything. Early settlements naturally gravitated towards the winding paths of rivers, it just made sense. These flowing waters weren't just a convenient place to live, they were the very veins of life, providing the precious water for growing crops, offering a ready-made pathway for trade and movement, and ensuring the sheer survival of a community. But as dependable as rivers seemed, they carried a wild, unpredictable side. One moment, they offered sustenance, the next, they could swell without warning, bringing devastating floods that wiped away homes and fields. To deal with such a powerful, dual-natured force, people quickly realized they couldn't just manage things on their own, individually. It demanded a collective effort, a careful coordination among many hands. Slowly, almost imperceptibly at first, the act of writing began to stretch its wings, moving beyond the simple tallying of goods and accounts. It wasn't just for keeping track of grain or livestock anymore. Instead, people started using these new symbols to capture something far more profound: stories. Take for instance, ancient epic tales, like the famous Epic of Gilgamesh. They delved deep into the very core of what it meant to be human, wrestling with big ideas like the deep bonds of friendship, the inescapable reality of our own mortality, and that primal, gnawing fear of death that touches us all. What's truly striking about these age-old narratives is how incredibly relevant those themes still feel to us today. It's almost as if, despite all the technological marvels we've invented and the rapid pace of change in our tools and gadgets, the fundamental worries and joys of the human heart haven't really shifted all that much. We might have faster computers and space travel, but we still grapple with loss, cherish our friends, and wonder about what comes next, just as those ancient people did. In the early days of many societies, looking up at the night sky was far from a mere philosophical pastime, it was deeply, crucially practical. Careful observation of the stars and planets actually helped people predict the turning of the seasons, which was vital for farming, and even gave clues about when the big river floods might arrive. Priests and scholars, those who dedicated themselves to studying the cosmos, spent countless hours meticulously mapping the journeys of the planets across the heavens. They didn't yet have the scientific understanding of the physics that explained why these celestial bodies moved the way they did, but they were incredibly adept at recognizing and charting their predictable patterns. This patient, detailed work laid foundations for so much more. From this dedicated sky watching, the very first calendars gradually took shape. People noticed the regular phases of the moon and the significant points of the sun's journey, like the solstices, and these celestial rhythms provided a natural structure for their lives. These observations dictated when to plant crops, ensuring they made the most of the fertile seasons, and when to prepare for the harvest. In a world without mechanical clocks or intricate timepieces, the heavens themselves became the ultimate timepiece, a grand cosmic mechanism. Long before anyone dreamed of gears and springs measuring out the hours, time itself was quite literally read directly from the vast, star-studded canvas above. It was an ingenious, elegant solution to the human need for order and prediction. While empires certainly grew larger and asserted their dominance through military conquest, they were also, perhaps even more importantly, intricate networks of exchange. Think about the famous Roman roads. These weren't just pathways for legions of soldiers to march swiftly to new territories, they were bustling arteries that facilitated the movement of so much more. Along these well-maintained routes traveled merchants, carrying goods from distant lands, teachers, sharing new ideas and philosophies, and engineers, spreading innovative techniques. The very concept of law, the privileges and responsibilities of citizenship, and different approaches to governance all flowed along these roads, moving hand in hand with pottery, spices, and other material goods. It was a constant intermingling of cultures and concepts, shaping the world far beyond the reach of any single battle. When the powerful Western Roman Empire eventually began its long, drawn-out decline, the consequences were felt across vast stretches of Europe. The complex infrastructure that had once unified the region started to crumble in many places. The well-worn trade routes, once so active, grew weaker and less reliable. During what's now known as the Islamic Golden Age, a remarkable period of flourishing intellect, scholars made incredible strides. They diligently translated ancient Greek texts, ensuring that precious knowledge from the classical world wasn't lost. They expanded the field of algebra, pushing its boundaries with innovative approaches, and refined astronomy to an astonishing degree. Their work in medicine also saw significant advancements, improving treatments and understanding of the human body. Observatories, equipped with increasingly precise instruments, were built to meticulously track the movements of planets, achieving a level of accuracy that was truly impressive for the time. This vibrant era clearly demonstrated that the preservation and expansion of human knowledge is a powerful, dynamic process that is rarely, if ever, confined to just one culture or corner of the world. It thrives on exchange and curiosity. Meanwhile, on the other side of the globe, in China, a series of groundbreaking inventions completely reshaped both communication and warfare. The creation of paper, for instance, revolutionized how information could be recorded and shared. Then came printing, which allowed texts to be reproduced much more quickly and widely, accelerating the spread of ideas and literacy centuries before anything similar would appear in the West. And of course, there was gunpowder, an invention that fundamentally altered the nature of conflict and military strategy. Movable type, a key innovation in printing, made it possible for books and documents to circulate far more broadly, essentially kicking off an information revolution long before the advent of the Internet. These inventions weren't just clever tricks, they were fundamental shifts in how human societies functioned. Looking back on history, it often feels like a neat, linear progression, one event leading logically to the next, like following a straight line. But for the people actually living through those times, the future was anything but clear. It was a swirling cloud of uncertainty. Kingdoms, great and small, would rise to power with fanfare, only to fall again, sometimes abruptly, sometimes slowly decaying. Borders, which we now see so clearly on old maps, were constantly shifting, fluid and contested. Plagues, terrifying and incomprehensible, would strike without warning, decimating populations and leaving profound scars. Yet, through all these tumultuous changes and human dramas, the steady, unchanging rhythm of the stars continued above. They moved with their silent, patient grace, oblivious to the restless, ever-changing world below. It was a stark contrast between human chaos and cosmic order. Then, in the 14th century, a tiny, unseen enemy began its devastating journey. A specific bacterium, carried silently by fleas, hitched rides on the well-worn trade routes, spreading out from Asia and making its way inexorably into Europe and beyond. This terrifying illness, which would come to be known as the Black Death, didn't move like an army, it spread like a creeping shadow, leaping from port to port, then infiltrating from village to village. It traveled with a horrifying speed, far faster than the medical understanding of the day could possibly hope to comprehend, let alone contain. People simply had no idea what was happening or how to stop it, making the crisis even more profound and terrifying. Entire communities, once bustling with life, found themselves eerily emptied, sometimes within a matter of months. The scale of the loss was staggering. In some regions, a third, or even more, of the entire population simply perished. Fields, once diligently tended, lay fallow and overgrown. Workshops that had once echoed with the sounds of labor fell silent, their tools gathering dust. The familiar, comforting rhythm of everyday life, the predictable cycles of work and community, were abruptly shattered, replaced by a pervasive sense of uncertainty and overwhelming fear. It was a rupture in the very fabric of society, a wound that would take generations to heal. And yet, despite the unimaginable devastation, the aftermath of the Black Death unexpectedly reshaped society in profound ways. With so many lives lost, labor became incredibly scarce. This sudden shift gave surviving workers a rare and powerful leverage. They could now demand better wages and improved conditions, something almost unthinkable before the plague. The long-standing, rigid social hierarchies, which had seemed so entrenched for centuries, began to weaken and show cracks. This crisis, as utterly devastating as it was, inadvertently altered the fundamental economic and social balances not just within individual nations, but across entire continents, paving the way for new structures and ways of thinking. In the centuries that followed, particular regions of Europe began to experience a vibrant resurgence, a renewed and passionate interest in art, the burgeoning fields of science, and the classical knowledge that had been preserved from ancient Greece and Rome. This remarkable period, which later historians would famously dub the Renaissance, wasn't some sudden, explosive awakening that happened overnight. Instead, it was a much more gradual and subtle shift, a slow turning away from dogma and towards a profound embrace of direct observation, rigorous inquiry, and a deep appreciation for human potential. It was an intellectual tide slowly but surely beginning to turn. Artists during this time, like the incomparable Leonardo da Vinci, weren't content with merely sketching what they saw. They took their curiosity to an entirely new level, actually dissecting human cadavers. Their goal was deeply scientific. They wanted to meticulously understand the intricate network of muscles and bones that lay beneath the skin, to truly grasp how the human body functioned. This pursuit of accuracy became a central, driving goal in their work. The natural world, which for so long had been viewed primarily through a symbolic or allegorical lens, was now something to be studied directly, to be explored with scientific rigor, and to be represented with an unprecedented faithfulness to reality. It was a profound change in perspective. At the very same time, a new breed of courageous navigators began to set sail, venturing bravely across vast, uncharted oceans. These ambitious voyages weren't just about discovery, they were about connecting continents in a way that would fundamentally and permanently link the entire globe. While these expeditions certainly opened up incredible new avenues for trade and expanded humanity's collective knowledge of the world, they also, tragically, carried a darker side. They inadvertently spread devastating diseases to new populations and, all too often, triggered brutal campaigns of conquest. The world, through these daring journeys, quite literally grew larger in scope, yet paradoxically, it also became far more entangled, a complex web of interconnected fates and consequences. In the year 1543, a quiet but utterly revolutionary idea was put forth by Nicholas Copernicus. He proposed, with compelling mathematical arguments, that it was actually the Earth that moved around the Sun, rather than the other way around, as had been believed for millennia. This wasn't a revolution of swords and armies, but a profound shift in thought, a silent overturning of a deeply ingrained worldview. His work effectively moved humanity from what we had long considered the undisputed center of the cosmos, placing us instead on just one planet among many, quietly orbiting a star that was itself just one of countless others. It was a humbling, yet liberating, new perspective. Later on, the brilliant Galileo Galilei pointed his newly perfected telescope towards the planet Jupiter, and what he saw through its lens provided tangible, irrefutable evidence that challenged long-held beliefs. He observed not just one, but 4 small moons clearly orbiting Jupiter, rather than orbiting Earth. This direct observation was a powerful blow to the geocentric model, the idea that everything revolved around our planet. It demonstrated, with simple clarity, that not everything in the heavens necessarily circled Earth. This period marked a critical turning point. Careful measurement and direct observation were beginning to successfully challenge assumptions that had been inherited through centuries of tradition and philosophical decree. It was Johannes Kepler who eventually described the true nature of planetary orbits, revealing them not as the perfect, idealized circles that many had long imagined, but as elegant, slightly squashed ellipses. This was another significant departure from purely philosophical ideas about cosmic perfection. The universe, it turned out, didn't conform to some preconceived notion of idealized geometry or aesthetic symmetry. Instead, it meticulously followed precise mathematical laws, principles that could be uncovered and understood through diligent data collection and careful analysis. This realization reinforced the growing understanding that the cosmos operated on discoverable rules, not just divine whim or aesthetic preference. Then, in the 17th century, the towering figure of Isaac Newton arrived and, in a stroke of genius, unified our understanding of motion. He brilliantly connected the everyday phenomenon of an apple falling to the ground with the majestic, grand motion of the moon orbiting Earth, all under his single, powerful law of universal gravity. What this meant was profoundly simple yet revolutionary. The humble apple and the distant moon obeyed precisely the same underlying principles of physics. For the very first time in human history, the vast, seemingly inscrutable cosmos suddenly felt comprehensible. He brilliantly connected the everyday phenomenon of an apple falling to the ground with the majestic, grand motion of the moon orbiting Earth, all under his single, powerful law of universal gravity. What this meant was profoundly simple yet revolutionary. The humble apple and the distant moon obeyed precisely the same underlying principles of physics. For the very first time in human history, the vast, seemingly inscrutable cosmos suddenly felt comprehensible. Then, form a logical hypothesis to explain what you've seen. Next, rigorously test that hypothesis through experimentation and evidence. And finally, be prepared to revise your understanding if the evidence demands it. This iterative process meant that knowledge was no longer a static body of facts, it became something dynamic, something that could be built up layer by layer, constantly corrected, and progressively improved upon over the course of time. It was an engine for continuous learning. As the 18th century dawned, a new kind of machine began to appear, capable of a revolutionary trick, converting raw heat directly into powerful motion. These were the early steam engines, and they started to transform industries. They were put to work pumping water out of deep mines, allowing access to more valuable resources, and soon, they began to power the very first factories. This remarkable shift meant that the stored energy of ancient sunlight, captured long ago by primeval plants and then slowly compressed over eons into coal, could suddenly be unleashed. This potent, concentrated energy was now at humanity's disposal, providing the muscle to drive burgeoning industries on an unprecedented scale. It was a quiet revolution that would change the world forever. With the advent of these factories, workers, who had for centuries been scattered across rural landscapes, began to gather together in rapidly growing cities. Urban population swelled dramatically, almost overnight. The streets, once relatively quiet, grew louder and more chaotic, filled with the clamor of industry and human activity. The air grew thicker, heavy with the smoke billowing from countless chimneys. For the very first time in human history, a significant portion of people no longer found their primary work in tending the soil, as generations before them had done. Instead, their lives revolved around the rhythm and demands of machines, a profound shift in the human relationship with labor and the environment. Soon after, railways began to crisscross the land, effectively stitching continents together with their iron tracks. What had once been a weeks-long journey by horse and carriage, a slow and arduous trek, could now be completed in a mere matter of days by train. Distance itself, rather than being a fixed geographical measure, began to shrink in terms of the time it took to traverse it. This new speed also meant that the old ways of organizing life, tied to the natural rhythms of the seasons, started to give way to rigid, predictable schedules. Timetables became the new organizing principle, dictating the pace of commerce, travel, and even daily life. Then came electricity, a truly invisible force, yet even more transformative. Unlike the bulky steam engines that needed to be close to their power source, electricity could travel silently along thin wires, reaching into homes and factories alike. Light bulbs, brilliant and revolutionary, extended the productive day far beyond sunset, allowing work and leisure to continue into the night. Telegraph signals, a marvel of instant communication, could now cross vast oceans in mere minutes, connecting distant continents almost instantaneously. This meant that for the first time, communication wasn't tied to the physical movement of people or letters. It detached itself from transport, opening up a whole new realm of possibilities for human connection and information exchange. Medicine, too, underwent a profound transformation. The groundbreaking germ theory finally revealed that invisible, microscopic organisms were actually the culprits behind many diseases, a revelation that shattered centuries of misconceptions. This newfound understanding paved the way for truly effective interventions. Vaccination became possible, providing protection against dreaded illnesses. Sanitation practices improved dramatically, reducing the spread of pathogens. And later, the discovery of antibiotics offered powerful new weapons against infections. Together, these advances gradually but steadily reduced mortality rates from diseases that had once been common, terrifying, and almost universally deadly. It was a massive leap forward for human health and longevity. In 1903, an incredibly fragile contraption of wood and fabric, an early aircraft, somehow managed to lift itself off a windy field. It stayed airborne for a mere 12 seconds. The Wright brothers, who had achieved this impossible feat, could never have truly predicted just how rapidly flight would evolve in the decades that followed, but they had definitively proven a monumental point: human beings, with their ingenuity and determination, could indeed rise into the air under their own power. It was a small beginning, a tiny hop, but it opened up the skies and ignited a dream that would reshape global travel and human perspective. Only 6 short decades after that first brief flight, humanity wasn't just leaving the ground, we were leaving the entire planet. It was a staggering leap. The same century that had begun with the commonplace sight of horse-drawn carriages clip-clopping down dusty roads somehow concluded with actual human footprints left on the surface of the moon. The sheer pace of technological and scientific change during that 100-year span was truly astonishing, almost beyond belief. It felt like the boundaries of what was possible were being rewritten at an ever-accelerating, dizzying rate, demonstrating humanity's incredible capacity for innovation. Yet, amidst all that breathtaking progress, the 20th century also brought with it an immense, horrifying capacity for destruction. 2 devastating world wars tore across the globe, fundamentally reshaping not only geographical borders but also the very fabric of societies. These conflicts laid bare both the incredible power and the terrifying danger inherent in advanced industrial technology. It became clear that human ingenuity, while capable of wondrous advancements, also carried the potential for unimaginable suffering. Progress and peril, it seemed, advanced inexorably, side by side, in a stark and heartbreaking duality. Then, in 1969, when the Apollo 11 mission successfully landed on the Moon, a human being had the extraordinary privilege of looking back at Earth from a truly unique vantage point. What they saw was a small, delicate blue sphere, suspended beautifully in the vast, inky blackness of space. From that cosmic distance, all the borders that so fiercely divided humanity on the surface were utterly invisible. Storm systems swirled gently, like brushstrokes on a canvas. The planet, in that profound moment, appeared both fragile and remarkably unified, a single precious gem in the cold expanse, offering a perspective that transcended all earthly divisions. At the dawn of the 20th century, the established world of physics suddenly found itself in a quiet but profound crisis. The well-understood laws that so beautifully described the motion of falling objects and the graceful orbits of planets worked perfectly on large, everyday scales. However, when scientists began to peer deeper, investigating the nature of light and the behavior of incredibly small particles, strange, unsettling discrepancies started to appear. Something fundamental, it became clear, was incomplete in their understanding. The universe, at its most basic level, was hinting at secrets that the old physics couldn't explain. It was Albert Einstein who bravely stepped forward with a radical new idea. He proposed that space and time weren't just separate, rigid backdrops against which events unfolded. Instead, he suggested, they were intrinsically linked, forming a flexible, dynamic fabric he called spacetime. According to his theory of general relativity, massive objects, like gargantuan stars and immense planets, actually bend and warp this very fabric. And it's this subtle curvature, this gentle dimpling in the weave of spacetime, that we experience every day as the force we call gravity. It was a profoundly elegant, almost poetic, reimagining of one of the universe's most fundamental forces. Following this new view, the Earth doesn't simply orbit the Sun because it's being pulled by some invisible, traditional force, like a rope tethering two objects. Instead, it's actually following the curved geometry, the invisible slope, that the Sun's immense mass has created in spacetime around it. Imagine rolling a marble on a stretched sheet with a bowling ball in the middle. The marble naturally curves inward. In a similar, but far more complex, way, our planet is simply moving along the inherent shape of spacetime itself, a path dictated by the presence of its much larger neighbor. It's a beautifully subtle dance orchestrated by the universe's fundamental structure. Around the very same period, another equally profound revolution was unfolding, but this one was happening at incredibly tiny scales, far smaller than anything visible. Experiments began to show bewildering results. Sometimes, particles, which we typically think of as solid little bits, behaved uncannily like waves, spreading out and interfering with each other. And conversely, waves, which are usually thought of as smooth ripples, sometimes acted like distinct particles. This baffling, counterintuitive behavior meant that reality itself, at the quantum level, simply refused to conform to our common sense or everyday intuition. It was a completely new and strange realm of existence. Quantum mechanics, the new framework that emerged to describe this microscopic realm, revealed a world governed not by the precise certainties we were used to, but by probabilities. Instead of having exact positions and perfectly predictable trajectories, particles at this level seemed to exist in states of likelihoods and distributions, almost like a cloud of possibilities. The microscopic universe, it turned out, was far less like a meticulously engineered clockwork machine, ticking along with perfect precision, and much more like a vibrant, shimmering field of potential outcomes, where absolute certainty was an elusive dream. It was a complete paradigm shift in how we understood fundamental reality. These two monumental frameworks, Einstein's theory of relativity and quantum theory, both proved to be extraordinarily accurate within their specific domains. Relativity perfectly described the grand cosmic ballet of planets and galaxies, while quantum theory masterfully explained the bizarre dance of particles at the subatomic level. And yet, despite their individual successes, they remained stubbornly difficult to reconcile, to weave into a single, unified, coherent description of nature that could encompass everything from the smallest subatomic particle to the largest galaxy. The exciting, persistent search for that ultimate unification continues to this very day, a grand quest at the heart of modern physics. Meanwhile, in the realm of astronomy, scientists were busy examining light from distant galaxies, and they began to notice something truly remarkable. The light reaching them wasn't quite as they expected. It was consistently shifted towards the red end of the spectrum, much like the pitch of a siren dropping as it moves away. This redshift was a clear indication that these far-flung galaxies were actively moving away from us, steadily receding into the depths of space. This pivotal observation provided compelling evidence that the universe itself, on its grandest scales, was not static but was actively and continuously expanding. The farther away a particular galaxy appeared to be, the faster it seemed to be rushing away from us. This consistent relationship wasn't just a curious anomaly, it strongly suggested that space itself wasn't just expanding from a single, central explosion point, but rather that it was stretching uniformly, like an inflating balloon, across incredibly vast distances everywhere. This concept of cosmic expansion, once a theoretical idea, suddenly became a measurable and undeniable reality, transforming our understanding of the universe's dynamic nature. It showed us that the cosmos was not a static stage, but a continuously evolving entity. Later observations brought an even more astonishing revelation. Scientists had generally expected that the expansion of the universe, influenced by the mutual gravitational pull of all matter within it, would gradually be slowing down, like a ball thrown upwards against gravity. Instead, to their utter surprise, the expansion appeared to be accelerating. It was as if space itself carried some subtle, inherent pressure, an unseen force actively pushing it outward, causing it to inflate ever more rapidly. This unexpected discovery threw open new questions and hinted at unknown components of the cosmos. To try and account for this mysterious, accelerating expansion, scientists introduced a new concept, dark energy. This term, in many ways, serves as much to describe the extent of our current ignorance as it does to quantify a measured phenomenon. Whatever this dark energy truly is, it appears to be the dominant force shaping the large-scale behavior of the entire cosmos, quietly but powerfully dictating its ultimate fate. It represents one of the biggest puzzles in modern cosmology, a profound mystery lurking in the very fabric of reality, waiting to be fully understood. Long before the startling discovery of dark energy, astronomers had already stumbled upon another profound cosmic mystery. When they meticulously measured how fast stars were orbiting within galaxies, the numbers simply didn't add up. The stars located in the outer regions of these galaxies were moving far too quickly, orbiting at speeds that suggested they should have long since flown off into space. The visible matter alone, all the stars, gas, and dust that we can actually see and measure, simply wasn't enough to provide the gravitational pull needed to hold them in such tight, rapid orbits. It was a glaring discrepancy. If only the stars and gas that we can visually detect were present in galaxies, those magnificent celestial structures should, logically, have gradually torn themselves apart as their outer components spun away. But instead, they remained remarkably stable, holding their elegant forms across billions of years. This fundamental discrepancy, this undeniable puzzle, strongly suggested that there had to be an unseen form of matter at play, providing a significant amount of additional gravity, quietly and invisibly holding galaxies together against the forces that would otherwise rip them asunder. It was a powerful hint at something truly unknown. This invisible component, the missing gravitational glue, is what we now refer to as dark matter. It doesn't emit any light, it doesn't reflect light, and it doesn't absorb light in any way that we can currently measure with our instruments. Essentially, it is utterly transparent to all the conventional ways we interact with matter. We can only detect its presence indirectly, primarily through its subtle but undeniable gravitational influence on the visible matter we can observe, and also by observing how its gravity bends the path of light coming from incredibly distant objects, a phenomenon known as gravitational lensing. Observations of massive galaxy clusters, for example, frequently reveal strange, distorted arcs of light stretching across the images. These aren't just cosmic coincidences, they are the telltale signs of gravity bending the paths of photons traveling towards us from even more distant galaxies. The extent of this bending, the degree to which the light is warped, indicates a far greater amount of mass present in these clusters than what our telescopes can directly observe as stars or gas. This provides compelling, visual evidence that something unseen, some invisible mass, is clearly present and exerting a powerful gravitational pull in these colossal structures. Calculations suggest that dark matter appears to outweigh all the ordinary matter, the stuff that makes up stars, planets, and us, by a ratio of roughly 5-to-1. Without this immense, unseen gravitational scaffolding, the intricate cosmic web of galaxies and clusters, the large-scale structure of the universe as we know it, would likely never have formed in the way it did. Galaxies might have remained smaller, more diffuse, and far more sparse. In essence, the universe would look profoundly, strikingly different, a testament to the quiet, pervasive influence of this mysterious substance that we still cannot directly see. Despite many decades of dedicated research and countless experiments, scientists have still not managed to directly detect an individual dark matter particle. The search continues with intense focus and ingenuity. Experiments, often located deep underground in shielded laboratories, meticulously search for incredibly rare interactions that might signal the presence of a dark matter particle. Meanwhile, powerful particle accelerators, like the Large Hadron Collider, attempt to create and identify candidate particles that fit the theoretical descriptions of dark matter. For now, the mystery remains stubbornly open, a grand challenge at the forefront of astrophysics and particle physics. Meanwhile, powerful particle accelerators, like the Large Hadron Collider, attempt to create and identify candidate particles that fit the theoretical descriptions of dark matter. For now, the mystery remains stubbornly open, a grand challenge at the forefront of astrophysics and particle physics. The gravitational pull becomes so extraordinarily strong that nothing, not even light itself, can escape its grip, creating a boundary known as the event horizon, a point of no return. And it turns out that at the very heart of most galaxies, including our own magnificent Milky Way, resides a supermassive black hole. These colossal giants are truly awe-inspiring, capable of containing the mass of millions or even billions of our Sun, yet paradoxically, they occupy a region of space that is actually smaller than our entire solar system. They are the quiet, powerful anchors around which entire galaxies whirl, their immense gravity shaping the dynamics of billions of stars, a testament to the extreme conditions that can exist in the cosmos. When matter, whether it's gas or stars, begins to spiral inwards towards a black hole, it doesn't just fall directly in. Instead, it often forms a rapidly rotating disk of material, an accretion disk, which heats up to extreme temperatures due to friction and compression. Before this matter finally crosses the event horizon and disappears forever, it can shine with an intensity that is truly staggering, radiating more brightly than entire galaxies combined. This incredibly luminous phenomenon is what astronomers observe as quasars, some of the most powerful and distant beacons in the universe, silent testaments to the violent processes around black holes. A truly landmark moment arrived in 2019 when astronomers unveiled the first direct image of a black hole's shadow. This wasn't a crisp, detailed photograph in the everyday sense, like a snapshot of a person, but rather a remarkable achievement of a global network of telescopes, working together as a single, Earth-sized observatory. The image, a dark silhouette against a ring of glowing matter, provided stunning visual confirmation of predictions about black holes that had been made over a century earlier by Albert Einstein. It was a powerful testament to the enduring accuracy of theoretical physics and the ingenuity of human observation. For the vast majority of human history, the familiar planets within our own solar system were the only worlds we knew existed, the entirety of our planetary neighborhood. That key understanding began to change dramatically in the 1990s, a pivotal decade when astronomers finally confirmed the existence of the very first planet orbiting a star much like our Sun, but far, far away. Since that groundbreaking discovery, the pace of exoplanet findings has multiplied rapidly, opening up a whole new cosmos of potential worlds and fundamentally altering our perception of planetary prevalence. Many of these exoplanets are unlike anything we have encountered in our own solar system, showcasing the incredible diversity of planetary formation. Some are dubbed hot Jupiters, colossal gas giants, much like our own Jupiter, but caught in incredibly tight orbits, circling extremely close to their parent stars, making them scorching hot. Others are rocky super-Earths, several times more massive than our home planet, where the crushing gravity would be immense and the atmospheres likely thick and alien. These discoveries constantly challenge our preconceived notions of what a planet can be. Astronomers often detect these distant worlds using an ingenious method. They carefully watch for tiny, almost imperceptible dips in the brightness of a star's light. These subtle changes occur when a planet happens to pass directly in front of its star from our perspective, temporarily blocking a minuscule amount of light. This precise measurement allows researchers to determine a planet's size and its orbital period with remarkable accuracy, providing crucial clues about these unseen companions. In some truly fascinating cases, scientists are able to go a step further. As a planet transits in front of its star, a tiny sliver of starlight can filter through the planet's atmosphere, if it has one. By meticulously analyzing this filtered starlight, specifically looking at which wavelengths of light are absorbed, researchers can identify the presence of specific molecules. This allows them to effectively taste the atmospheric composition, potentially revealing the telltale signatures of water vapor, methane, or even carbon dioxide, offering tantalizing clues about the potential habitability of these distant worlds. It's like reading the chemical fingerprint of an alien sky. A small, but incredibly exciting, fraction of the exoplanets discovered so far orbit within what scientists call the habitable zone. This is the specific range of distances from a star where temperatures on a planet's surface might be just right to allow for the existence of liquid water. Of course, the presence of water doesn't automatically guarantee life, but here on Earth, it has proven to be absolutely essential to every single known organism, from the smallest microbe to the largest whale. So, finding liquid water on an exoplanet is always a tremendously hopeful sign in the search for life beyond our home. Closer to home, within our very own solar system, scientific attention has increasingly turned towards the intriguing icy moons that orbit our gas giants. Beneath the frozen crust of Jupiter's moon Europa, for example, there is compelling evidence suggesting the presence of a vast, subsurface ocean of liquid water, kept warm by tidal forces. Similarly, Saturn's moon Enceladus actively ejects dramatic plumes of water vapor and organic molecules into space, strong indicators that it, too, harbors a hidden ocean beneath its icy shell. These moons, once thought to be barren, are now considered prime candidates in the search for extraterrestrial life. Mars, our planetary neighbor, might seem cold and desolate now, but billions of years ago, it was a far warmer and wetter place. Its surface still bears clear evidence of a more temperate past, with ancient river valleys carved into its landscape and the undeniable remnants of old lakebeds. Today, a fleet of robotic rovers diligently explores its dusty surface, carefully analyzing rocks for chemical signatures. These faint, lingering traces might just hint at the presence of past microbial life, whispering stories of a bygone era when the red planet may have harbored a vibrant, if simple, biology. The search for life beyond Earth is, by its very nature, a careful, meticulous, and incredibly patient endeavor. Scientists aren't looking for definitive proof of alien organisms. Instead, they are searching for subtle patterns, chemical anomalies, or complex structures that are highly unlikely to arise from non-living chemistry alone. Even the discovery of a single, simple microbe somewhere beyond Earth would be a truly profound event, fundamentally transforming our understanding of biology itself and, perhaps most importantly, completely redefining our place, as humans, within the grand tapestry of the universe. If intelligent life does indeed exist somewhere else in the vast cosmos, the sheer distances between stars pose an extraordinarily difficult challenge to any hope of communication. Even signals traveling at the fastest possible speed, the speed of light, would take years, or more likely, centuries, to successfully cross the immense interstellar gap separating star systems. The universe, despite its interconnectedness through gravity and fundamental laws, is also incredibly vast and silent, making any direct conversation with distant intelligences a formidable, almost daunting, proposition. It's a universe connected, yet simultaneously isolating. Still, the possibility of life, even intelligent life, remains wide open. In a universe that contains literally hundreds of billions of galaxies, and each of those galaxies containing billions of stars, even events that are incredibly rare on a local scale could easily occur many, many times across the cosmic expanse. So, the question isn't just a simple, whether life exists elsewhere, but rather, a deeper inquiry: how often does complex life, or even intelligence, manage to emerge from the raw materials and processes of the cosmos? It's a profound numerical and philosophical puzzle that continues to inspire astronomers. Among all the astonishing phenomena the universe has managed to produce over billions of years, the emergence of consciousness remains, perhaps, one of the most intriguing and mysterious. Inside the human brain, an unimaginably complex organ, roughly 86 billion neurons communicate with each other through a constant ballet of electrical and chemical signals. These intricate interactions, firing in precise sequences, form incredibly complex networks that give rise to our inner world. It's truly a marvel of biological engineering, packed into a relatively small space. From these intricate patterns of activity within this living circuitry, something truly profound emerges: our thoughts, our cherished memories, and the rich tapestry of our emotions. Unlike the silent, objective existence of stars or galaxies, consciousness turns inward. It allows matter, the very atoms and molecules that make us up, not just to passively exist, but to actively experience its own existence, to observe, to feel, and to reflect. It's a unique and special property, a window into an internal universe, making us the universe's way of knowing itself. Over the long sweep of human history, we gradually developed external memory systems. First, there was writing, allowing thoughts to persist beyond a single mind. Then came libraries, vast repositories of collective knowledge, and now, sophisticated digital storage. This evolution meant that precious knowledge, which had once been fragile and vanished with the death of individuals, could now persist across centuries, growing and accumulating. Culture itself, in this sense, became a powerful extension of our individual and collective cognitive abilities, a way to build upon the wisdom of generations. If you hold the entire history of the universe in your mind once more, it no longer feels like a frantic chain of dramatic, isolated events. Instead, it feels like a single, incredibly slow unfolding, a long, patient breath taken across billions upon billions of years. It's a testament to the universe's own profound sense of time and rhythm, an unhurried, majestic cosmic dance. From the very first moment of expansion to the formation of the first stars, from the swirling galaxies to the coalescing planets, from the bubbling oceans to the emergence of conscious awareness, each astonishing step followed naturally and logically from the last. Nothing in this grand cosmic narrative appeared suddenly, without a prior cause or a preparatory stage. It was a continuous, elegant chain of causality. Even the profound uncertainty inherent in quantum mechanics, the subtle fluctuations at the smallest scales, were an integral part of that continuous unfolding. Tiny, seemingly insignificant variations in the early universe eventually became the seeds for colossal galaxies. Subtle asymmetries in the primordial matter gradually led to the existence of more matter than antimatter, allowing the universe to exist as we know it. And now, those very same particles, born in the universe's fiery crucible, rest in quieter, more structured forms, in the solid rock beneath your feet, in the flowing water you drink, and in the living cells that comprise your body. The early universe, in essence, still exists. It has simply transformed, transmuted, rather than being completely erased, its ancient components recycled into new forms. The future, too, will not arrive all at once, in a sudden, dramatic flash. Stars will gradually age and transform, their light slowly dimming. Galaxies will patiently drift apart, carried by the expanding fabric of space. The cosmos will not end with a sudden, abrupt extinguishing of light, but with a long, slow fading, a gentle descent into an epoch of profound, quiet darkness. Yet here, in this specific moment, warmth persists, radiated from our sun. Gravity holds you gently to the ground, a constant embrace. Air surrounds you, a life-giving envelope. And light from distant suns, some from galaxies far, far away, continues its silent, ancient arrival, bringing messages from across unimaginable cosmic gulfs, touching your eyes, connecting you to the universe. The universe does not demand that you understand all of it at once, in a single, overwhelming comprehension. It simply continues, immense and steady, pursuing its own grand processes, whether observed by conscious minds or not. It's an enduring, self-sufficient reality, grand beyond our full grasp, yet intimately connected to every aspect of our existence. And so, the story of the universe settles, not into a definitive ending, but into a profound and quiet continuity. The expansion of space goes on, relentlessly stretching the cosmic fabric. The stars shine on, their ancient light a steady beacon in the vast darkness. Time, that relentless river, moves on, carrying all of existence forward into an eternal future, an ongoing, never-ending saga. From a hot, incredibly dense beginning, a primordial fireball, to the vast and intricately structured present we inhabit, the universe has carried its immense energy forward without interruption, a continuous flow through billions of years. That profound continuity, that unbroken thread of cosmic existence, extends even to you, here and now, a living part of the universe's ongoing story. The night sky remains overhead, calm and incredibly patient, a vast canvas of stars. The galaxy, our magnificent Milky Way, turns unseen, its immense rotation imperceptible to our senses. The Earth rotates softly and steadily beneath your feet, carrying you through space. And the universe, immense and unimaginably ancient, continues its quiet, majestic unfolding, its grand story perpetually in progress.